back. I hope you all had a great 4th of July weekend. We are now on the third class, right? And each class represents about a week, right? So we're almost done. After today's class, we'll be done with all the material that will be covered on the first midterm. And that's a good thing because we will have the first midterm next week. The time that I have scheduled for the midterm is next Monday beginning at 6:30. So if you have a conflict with that time, please let me know. I can be flexible with the times, certainly to some extent if you have other commitments that'll keep you busy Monday evening. Obviously, if you have approved accommodations from the university, those will be honored in the class. And like I said, if you do need an alternate time to write, this may be a little easier to do in an online course versus something where we're writing exams in rooms. Because this is an online course, the exam will be online, and because it's not really it'll be an open book exam, right? That means that you can access any materials that are on my courses, any links to YouTube content that's already been created, any material that's available online with some restrictions. Particularly, it means, one second, I got somebody in the waiting room. Sorry about that, I didn't see you in the waiting room. So we're just going over the exam here, and it will be, good idea. So going over the exam information, so because it will be an online exam, the exam will be an open book exam where you have access to things like notes, even the posted solutions that are on my courses to homework problems. But that does not mean you're allowed to collaborate. You're not allowed to talk to other individuals in this class, other individuals who have taken this class in the past. You're not allowed to use things like pay for solution sites. So I think we all probably know some names of those types of websites. All of those things are academically dishonest. The purpose of the exam is to test your understanding of the material, right? So it has to be your work that you are submitting. There will be consequences as outlined here if it's determined that that you're cheating in this way, right? So I think everybody kind of knows what cheating is, right? So I will ask you not to cheat. One of the ways, this is not great. One of the ways that I've been trying to deal with this in online exams is to kind of have the exam be gated. Because those pay for solution sites, my understanding is that they promise turnaround for solutions on the order of 20 to 30 minutes. So what we'll be doing is the exam will have 3 different components. So 10 multiple choice questions, which you can access on a quiz format in my courses. So that quiz will open specifically for you at whenever time your exam begins. So nominally at 6:30 on Monday. And then you'll have nominally half an hour to do the problem. And I'll give you 5 minutes to access the material and press submit. So stuff that you don't have to do if you're in a room, right? And then we'll have 5 minutes where you can sort of take a break, relax a little bit, right? Recenter. And then you'll have access to the first long answer program or the first long answer problem. So again, for someone with standard time, that access to the first long answer problem would begin at 7:10 p.m. Again, nominally you'll have half an hour to do the problem, but of course you have to access the problem and then you have to upload it to a Dropbox. So you're given a little bit extra time for the long answer problems versus the multiple choice question. And then, so that will be, the submission time for that will be 7:50 p.m. And then the second long answer problem will become available 5 minutes after that. On-time submission will be 40 minutes after that, which would be 8:35 p.m. So all of this, I put up an announcement today on the My Courses website too, if you want to check that out. So there will be a 10% penalty for every 5 minutes material is submitted late, right? So for example, exam problem 2, I think this should mean the second problem, right? Or the first long answer problem. The due date for that is 7:50. So if you submit between 7:51 and 7:55, there would be a 10% penalty. Between 7:56 and 8 o'clock, an extra 10% penalty, right? So a total of a 20% penalty, etc. Plus, then you start eating into the time for the next problem. So that's basically how we're going to run the exam. I think that it's better to do early in the week, which is why I picked Monday, because we're going to keep sort of going over material. We'll go over new material today and then half of Thursday's class, and we'll keep the second half of Thursday's class open so that if you have any questions, we can kind of go over those. So usually before exams, sort of in person, what I do is I just book an office hour time in a classroom, and people can come in and kind of ask me anything, right? And I'll take one of our class times and do that. So I'll use half of our lecture time on Thursday just to field any questions that you have about the material that we've done so far. Again, notify me as soon as you can if you're going to have if you think you'll have a conflict with this 6:30 start time on Monday. And then also if you have approved accommodations, we'll still gate the exam in the same way. So we'll still release those different problems at different times, but obviously the timing will be different if one of your accommodations involves the time that you have to write the exam. So if you have approved accommodations that deal with extra time, I'd appreciate if you email me and we will figure out what's a good time for you to start the exam, because it might go really long otherwise, right? So for the short responses or the multiple choice, is there going to be chances for partial credit? No. So these will be A, B, C, D, E type questions. I know that that's sometimes frustrating as a student. You do get partial credit in long answer problems. I think that kind of reflects this idea that as engineers, we want to prioritize the process. That if you have a good process, then over the long term, you'll get good answers more frequently. But I think that the idea that multiple choice questions are right or wrong, kind of reflects the idea that, in engineering, if you are designing a rocket and there are people on that rocket and the rocket fails, there's no partial credit, right? So, or if a bridge falls down, right? There's real consequences to the things that we do as engineers. So I think the way that we do tests kind of reflects a little bit of that both ways. Oh, the long answer problems, certainly you will have, so you will be, you'll be given a problem, right? And you'll be expected to write your answer to the problem, right? And then when you write your answer to the problem, then you'll upload that to a Dropbox in My Courses, and then and that'll be graded. Yeah, so certainly that will not be binary. That will be about following the process, right? Which we'll talk about. We're going to do 2 long answer problem examples, basically today, maybe 3 actually, if we can squeeze it in. So those certainly will be partial credit. So I guess what you'll need to do is you'll have to have access to, I think the easiest might be if you have access to a printer, but if you don't, that's okay. Because you will want to have paper, right? So you'll want to, write your answer on paper, with something like CamScanner, turn it into a PDF, and then upload it to the website. Right? And that's sort of why you have more than half an hour to do the problems, why you have 40 minutes to do those problems, because you're sort of given 10 minutes to do the sort of administrative part of submitting the answer. A breakdown for each. So I believe, and I'll double check this, but I think that it's, so each multiple choice, so there's 10 multiple choice questions. I think each are worth 3 points, so that's worth 30 points. And the 2 long answer problems are worth 35 each. So that is not what I think, that's what I know. So that is the breakdown. So the multiple choice part of the problem is worth 30% of the midterm. Then the 2 long answer problems are each worth 35% of the midterm. So that should sum to 100. As we said earlier when we looked at the syllabus, which I don't have in front of me, each midterm is nominally worth 25% of your grade. But if you do better on the final than one of the midterms, I'll drop the lowest of the midterms and have your final count for, instead of 30%, have it count for 55%. So your first midterm could be worth 25% of your final grade, and it could be worth 0% of your final grade. But as always, it's good to bank the points, right? So if you get 100% on the first midterm, it's nice to be in a position where you have those 25 points, right? But if you don't have a great first midterm, it doesn't mean that the class is over, right? Because I'm a lot more interested in what you know at the end of the class versus what you know at this first checkpoint or even the second checkpoint. That makes sense? Any other questions about the exam? Okay. So today we're going to start putting stuff together. So, in the first lecture we talked about work mostly, and how do you find work, right? Excuse me, there's something beeping in my office. I'll be back in just a second. Sorry about that. Hopefully you don't hear that in the background. Yeah, it's kind of funny. I bought this toothbrush at BJ's, but they forgot to take that tampering thing off it. So my kids took it off, and it started to beep like crazy. So I submerged it underwater, figuring that would break it. But apparently that only broke it for 2 days, and it obviously just started in the middle of our class. So sometimes the universe feels like it's against you. And speaking of the universe, right, we've been talking about thermodynamics and trying to understand how the universe works, right? And we've been thinking particularly about the first law for closed systems, right? And I've been making the argument that the first thing we want to do is figure out if it's an open or closed system, right? So if we know that it's a closed system, which it will be, particularly for the long answer problems on the first midterm, and then when it's closed, we know we can use the closed version of the first law, which is that the change in energy in the system over time is equal to the heat in minus the work out. We can make some assumptions and turn that into the change in internal energy in the system is equal to the heat transfer in minus the work out, right? So this is common to probably any first law problem you're going to get on the long answer part of the exam. Now, maybe you'll have 2 different processes you have to deal with, but this part, every single time you're going to do this, right? Then you're going to say, oh, how do I find the work? Okay, the work is equal to the integral of pressure over volume, right? So if I can figure out the pressure-volume relationship, then I can find the work. But then how do I find the change in the internal energy, right? So on the left-hand side of my equation, the textbook, we're going to look a lot of these things up inside the textbooks, but the thing is we won't know the change in the internal energy. The textbook doesn't know that, but we can look up things like the change in the specific internal energy. And if we do that and multiply by the mass, then that'll give us the left-hand side of the equation. And then we can use the first law to find the heat transfer. So generally, that's what we're going to do. Now, a lot of times, the hard part about thermodynamics is this choose your own adventure, right? So now when we get to how do we fix the state, how do we find the change in internal energy, we have to ask ourselves, well, what kind of fluid is it? Is it subcooled liquid, or is it water, or is it an ideal gas? And even if we know that, we're not done, Because if it's water, we have to know, is it going to be a subcooled liquid or a two-phase mixture or a superheated vapor? So what's the phase? And then if it's an ideal gas, I got to know what assumptions I'm going to make about the specific heat. So am I going to say that it's constant specific heat, where delta U will just be CV times delta T? Or am I going to say it's variable specific heat, and I'm going to try to find that specific internal energy on a table? Now, eventually, as we progress through the course, we'll also have to figure out what to do on our flow chart here if it's an open system. But we don't have to do that yet, right? We're going to start thinking about that once we get, well, really to the end of this lecture, right? But the first half of today's lecture, probably more than half, is going to be going through examples with both water and ideal gases, right? So here's the first problem that we'll do together today, and it tells us that there's 2 kilograms of pure water in this piston cylinder assembly. The water is initially at 1 atmosphere and 20 degrees Celsius. Heat gets added to our system at constant pressure until the piston hits the stop. So what's happening is we're going to add heat, and that's going to make our fluid expand, which makes me think that this water is probably boiling, right? Because then as some of it turns to vapor, that vapor takes up more volume, right? And that's going to happen until the piston hits the stops, right? So then what happens, right? So we move from this distance L1 all the way to this distance L2. We keep adding heat until the pressure reaches 4 bar. We're asked to find the work, the heat transfer of the total process, so both processes together, and to sketch the TV and PV diagrams. So I'm going to start working this out on this Word document. So this is the same problem. All right, so one of the nice things, and I don't know if we talked about this too much in class, but I like to draw what I call a state table as we start to get into problems like this that have more and more given information. So in this problem, I have 3 states, right? I have my initial state, which I'm going to call state 1. In my initial state, I'm at this position L1. And then we add heat until we get to our intermediate state, state 2, where we're at the stops here, but we're only at still 1 atmosphere. And then we're going to get to state 3, where we're at the same volume. The piston doesn't move, but the pressure changes. Now, at these different states, there's some information I'm going to want to know. I'm going to want to know, say, the pressure. And I like to put units here. Now, this is one of the tips that I'll give you when you do these problems. If it's a metric problem like this one, I always try to put my pressures in kilopascals. Because it's going to make my life easier when we start to talk about work and I'm talking about kilopascals multiplied by change in volume, meters cubed. I'm going to get kilojoules, which is usually what I want there, right? So here they tell me at state 1, we're at 1 atmosphere, which is 101.3 kilopascals, right? And then we do this as and we can do this too. My temperature, which is going to be in degrees Celsius, this is going to be 20 degrees Celsius initially. Okay? And then we're going to want to know U, the specific internal energy, which is kilojoules per kilogram. And what we're going to see is we're also going to want to know what the volume is. Although maybe not the total volume, maybe the specific volume. Because here we want, if we can get it, we want to have these intensive properties. Because I know that I can fix a state if I have 2 independent intensive properties. So it's going to be meters cubed per kilogram. So here they tell us that we initially have a pressure and a temperature. We add heat, right? So here, if I was drawing on my diagram, and here again, this is probably not the most important picture for this problem, but I want to symbolize that heat's going in, right? So I know that heat in is positive, right? So as I'm adding heat, I keep the pressure the same until I hit the stops, but I don't really know anything else about this other state, right? It says heat is added until we hit the stops. Here, though, if I knew the volume, this is going to be V2 divided by the mass. Here we know we keep adding heat again until this becomes 400 kilopascals. And V3 is equal to V2. This is a little bit of tricky part here because it might not be immediately clear to you that the volume stays the same. That's one of the tricks we need for this problem, right? And then it asks us to draw TV and PV diagrams. Even though that's the last thing that it asks me here, oftentimes on a test, that'll be the first thing that we ask. So let's start with, I'm not going to know exactly where we are on this. I'm going to draw a PV diagram. Pressure versus, I'll say specific volume over here, right? Now, here, we're going to know that it's water. And because it's water, we can draw this vapor dome. Two kilograms of water. The water initially exists at 1 atmosphere and 20 degrees Celsius. Right? So here, I want to draw a constant pressure line that's 1 atmosphere. Oops, I thought I was drawing a TV diagram. All right, let's do this again. So we have a pressure versus volume diagram. I have my vapor dome. Right? And now I have a constant pressure of 1 atmosphere. Right? Which is 101.3 kilopascals. Now, this I might just know because I'm human that lives most of my life at 1 atmosphere and I know where water boils. But I could look it up on a table if I didn't. But if I wanted to draw the constant temperature line that's coincident with this constant pressure line under the vapor dome, this would be 100 degrees Celsius. Now, my temperature in my first state is not 100 degrees Celsius, it's 20 degrees Celsius. So I have to shift this temperature line down to draw something that's 20 degrees Celsius here. So this means that my first state, I'm expecting to be here as a subcooled liquid. So here, if I'm thinking phases, I'm thinking subcooled liquid. My second state, I know that the volume goes up, right? And because the mass stays constant, the specific volume goes up. So here's the thing. I know that state 2 is somewhere to the right here. It could be a two-phase mixture. It could be a superheated vapor. I don't really know. Right? So here, I don't know what the phase is. But I do know that once I move from state 2, my volume stays constant. So I can start to draw this diagram, but I can't really draw the whole thing yet. Right? But that's okay, it was part D. But I think sometimes when we do the sketches, it can be helpful to figure out what's going on. right? So at least I know here from drawing this that my state 1, I'm expecting that to be a subcooled liquid, right? Required information, I have to find the work, the total heat transfer, right? So this is going to be work, which is going to be work from 1 to 2 plus the work from 2 to 3. The total heat transfer, which is Q1 to 2 plus Q2 to 3. And then I want to comment on the direction. I already know that the heat should be positive. Do I already know the sign of the work? Or do I have enough information to find the sign of the work, you think? Yeah. Because the volume is increasing, right? Remember that work is equal to the integral of P dV. And this is absolute pressure. So the pressure is always positive. Right? So this, we're always going from state 1 to 2, or with the volume at the end minus the volume at the beginning. So if the volume is increasing, right? So if V goes up, then work is positive, right? That's the system is pushing out on the surroundings. And if the volume goes down, then the work is negative because the surroundings are pushing in, compressing that gas. Right? So here we know that the work should also be positive. So already we can do this. And this is the thing. Another thing that I kind of get sad about when I grade exams is you might get like that. Maybe it's part C or part D in a problem. Maybe it's worth 2 points. And it says, comment on the sign of the heat transfer. Right? Even if you didn't do any of the problem, you write down heat in is positive and heat out is negative. So you could say if the heat is positive, that means it's going into the system, right? Because then even if you didn't get a numerical answer, you've shown that you understand that part of the problem, right? So you always want to try to demonstrate as much of your understanding as you can. Right? I guess there's sort of schematic versions of these, and we've started to talk about the PV diagram. So I'll talk a little bit about the TV diagram. Those I often find a little easier to draw. So here we know that at 100 degrees is this 1 atmosphere line, right? That's when this is the pressure is equal to 1 atmosphere, right? And because our temperature is below that, it's like 20 degrees, which is not to scale on this thing. My state 1, so that's good. In both of these pictures, my state 1 is a subcooled liquid. Right? So this is subcooled liquid, this is superheated vapor over here, and this is two-phase. So I don't know, I know that as the volume is going up at constant pressure, I have to follow this line, but I guess technically it could still be a subcooled liquid, it could still be a two-phase mixture, it could still be a superheated vapor. Until I know the volume, I can't get that. Right? But it's either probably going to be something like this, or like this. And then again, as we move to the last state, it's got to be on one of these vertical lines. So we have to start to do some math to figure it out, right? But even before that, my argument for all of these long answer problems is do as much of the problem symbolically as you can. Because the symbolic part of the solution is basically the same no matter what the problem is. So if you can do the symbolic part of the solution, you can write that down. You probably get 15-20% of the points for the problem for that. And that's going to be the same for like every single problem. So that's like, you definitely want to do that, right? So here, our first governing equation is the first law, right? So we're assuming that it's a closed system. And because it's closed, this is my first law, right? But I'm going to say that it's, I'm going to neglect kinetic energy and potential energy. Oh, this should say spring energy, right? All of these I'm going to say are about equal to 0. Right? And if it's closed, then the mass is constant. So my first law over here becomes the mass times U at the end, right? minus, so u at the end, minus u at the beginning is equal to q minus w. Now there's two ways that I can think about this problem, and neither way is wrong because it didn't ask me for the specific parts. So I could either, say that mass times u2 minus u1 is equal to q 1 to 2 minus w 1 to 2. Or I could say that mass from u3 minus u2 is equal to q 2 to 3 minus w 2 to 3. Right? Or I could sum these up, and if I added these together, right, I've got positive u2 and negative u2, so I'd get the mass times u3 minus u1 is equal to q1 to 2 plus q2 to 3 minus w1 to 2 plus w2 to 3. And this right-hand side is equal to q1 to 3 minus minus w1 to 3. For the sake of this example, I'm going to break this down into the two constituent parts. Right? So I'm going to do it this way. And then when we get the totals, I'm going to use this, right? So I could call this maybe equation 1, equation 2, and equation 3. So when I look at these equations, right, I'm just going to focus on 1 and 2 for right now. I know that the mass is 2 kilograms. I know that heat is coming in positive, right? In work, these terms are positive, right? I don't know anything about these states yet. I haven't fixed the states, right? What we're usually trying to do in thermodynamics is get to a point where we have an equation where if we only could fix all the states, we would get the right answer, right? So in that flow chart that I was telling you about, I said, well, when you get these, remember this, right? That work, most of the time, is going to be the integral of P dV. Right? Now, there's a couple different ways that we can think about this, right? But in this case, when I drew my PV diagram, I had one process from state 1 to state 2 that was constant pressure, and one process that was constant volume. What do I know about the work when it's constant volume? Another way to think about this is the area under a PV diagram. So if I have a vertical line, I don't know if this is pointing up or pointing down necessarily yet, but does it matter? Right? Because it's a vertical line, I know that work from 2 to 3 is equal to 0 because the volume, V3 is equal to V2. So there's no work there. So that's pretty good. The other thing that I know is that the work from 1 to 2 is going to be equal to the integral from state 1 to state 2 of P dV. Now I need to know the pressure-volume relationship. So oftentimes I'm going to look for something like PV to some constant is equal to a constant. Right? In this case, they told us that pressure was constant, so N is equal to 0, and this just means that the pressure is equal to a constant, which means here I can say that the work from 1 to 2 is equal to some constant, the pressure, which I know, times the integral from state 1 to state 2 of dV. And this is my second favorite integral, right? My favorite integral, although maybe this is my favorite integral because even if I wrote this integral for the vertical line, it gets confusing, right? So this is probably my favorite one, right? That pressure times V2 minus V1 is equal to the work from 1 to 2. So my equation 1 here becomes the mass times U2 minus U1 is equal to Q from 1 to 2 minus W from 1 to 2. But that's going to be equal to Q from 1 to 2 minus pressure times V2 minus V1. My other equation, equation 2, is going to become M times U3 minus U2 is equal to Q2 to 3. That's it, because there is no work, right? Or I guess to be more explicit, I could say minus 0. So now we got a choice. We can move ahead with this problem trying to figure out V2 and V1 because neither of those is given to us. Or we can try to find these U's. Right? It doesn't really matter. In an exam problem, maybe it says like, oh, find the work. So you do the work first or whatever. But, you know, if you were just doing this at your job or something, it doesn't really matter which one you do first. So I'm going to figure out this part first. So I'm going to look for V2 and V1. So another way that I could write this, V2 minus V1, is the mass times the specific volume at 2 minus the specific volume at 1. Now, when I start to talk about specific volumes, this is, again, I'm starting to talk about like, oh, how do I fix the states? Right? So if I go back up to my state table, I think it told me that at state 1, we knew that the temperature was 20 degrees Celsius and the pressure was 101.3 kilopascals, right? And we said, oh, that means it's a subcooled liquid. Right, so if I'm trying to fix state 1, I know it's a subcooled liquid, right? Because, well, let's go through the whole flow chart here, right? So when I'm trying to fix a state, the first thing that I ask myself is what's the fluid? Right? And we really have two different options, water or something like it, or an ideal gas, right? But in this case, it's water. So I need to figure out at each different state, is it a subcooled liquid, a two-phase mixture, or a superheated vapor? Because that's going to tell me like what table I want to use. Right? But for state 1, I know it's a subcooled liquid. Now what we said the other day was for subcooled liquids, I'm going to assume that they're incompressible and then we're going to make the following assumptions. That U1, which is really a function, in this case of temperature and pressure, is approximately equal to UF at the same temperature. Because this incompressibility assumption means that things aren't really a big function of pressure. So as long as I can figure out the right temperature, which I'm told, then I can fix these states, right? The other thing that I want is specific volume of 1, which in real case is a temperature and pressure function. But we're going to say it's about U or VF of T1. So I'm going to go down. Let's see if hopefully I have the tables here. Right, so this is the table. This is from the FE handbook. So if you choose, you can, if you want to be a professional engineer and get like a stamp so you can stamp drawings and sort of take on that extra responsibility, there's 2 different exams that you have to write. One of them is sort of talking about your competency. So sometimes students will prefer to do that maybe when they're seniors, because then they haven't forgotten everything that they learned in university. They're still used to writing exams. But then you have to practice for a little bit. You have to be in industry for a little bit, get a bunch of experience. And then there's like a legal and ethical exam that you have to write. Right? But we can do the first one here. That's where these tables come from. Right? So here we can say that, oh, this is the equivalent of table A2 in the textbook. It's a two-phase table where the temperature is on the left. So we know that we have 20 degrees. So my specific volume is going to be VF, right? About 1 over 1,000. And my UF is going to be 83.95. So I can put that back into here. So this is going to be about 1 over 1,000 meters cubed per kilogram. And this is going to be, what I say, 83.5 or something? I think. Kilojoules per kilogram. But anyway, we have this information now. But how do I get this one? Right, so I can go back up to my state table, right? And I can see that at state 2, I know the pressure. And it sort of looks like that's the only thing that I know. But I actually know this length here. Right? So I might be able to use that length in this diameter here to tell me something about the volume that's here, right? So if I wanted to find the volume at state 2, so the volume at state 2 is going to be the cross-sectional area of my piston, right? Which is pi d squared over 4, right? Or pi r squared, right? Times L2. Now, I like to write this sometimes as pi r squared, times L2. Now, you can see that there's a reason I picked these numbers, because my diameter is 2 meters, so my radius is 1 meter, right? And my length is also 1 meter. So here, my math works out pretty good, right? Because this is going to be pi times 1 meter squared times 1 meter, right? So this is approximately 3.14 meters cubed. But what I really want when I'm trying to fix a state is the specific volume, which is going to be V2 over the mass. And I think we said that there's 2 kilograms of water in this problem. I should have made it 1, obviously, because then I could do the math in my head. Right, so this is going to be 3.14 divided by 2. So this is 1.57 meters cubed per kilogram. So now we know 2 things, right? So now and the pressure here at state 2 was still 1 atmosphere, or 101.3 kilopascals. So now I gotta ask myself, because I know it's water, I gotta ask myself, what's the phase? So I gotta look, there's 3 different options, right? So I can look and I can find VF, for at 1 atmosphere. And I can find VG at 1 atmosphere. If this specific volume here is in between these 2 numbers, then that means it's a 2-phase mixture. If it's below this number, then it's a subcooled liquid. And if it's above this number, then that means it's a superheated vapor. And maybe that makes more sense if we look at it up here on our diagram. Because we're saying we're at this 1 atmosphere constant pressure line. Right? Now, if I drew a vertical line down from here, this would be VF. A vertical line down here would be VG. So if my specific volume is in between these two numbers, then it's two-phase, because I'd be under the vapor dome. Right? But if it's bigger than VG on this line, then it would be like this point, and we'd be a superheated vapor. But if it was less than VF, well, that would be like state 1, and I'd be a subcooled liquid. Right? So now we have to see, right? We know, we already looked this one up, right? This is 1 over 1,000. So that means it's not going to be a subcooled liquid. But if I go back down to that table, and I look here, VG is 57.79. Right? So that's a pretty big number. 57.79. But we're at 1.57. So that means we're two-phase. Does that make sense? So when I'm trying to fix my state, now I know that it's two-phase. When it's two-phase, I would like to know what the quality is. I know it's true that for any property that's not temperature or pressure, so for a specific volume at state 2 of some quality x2, this is the equation follows my quality equation, where it's VF plus x2 times VG minus VF. Does that make sense? But really, in this equation, I know V2, right? Because that's this number here. I know VF and VG, so I'm trying to find x2. So this isn't exactly the form of the equation that I want yet. I'd like to write down that x2 is equal to V2 minus VF divided by VG minus VF. Right, so now I take 1.57 minus VF is about 1 over 1,000. Right, so this is 1.57 minus 1 over 1,000 divided by, what was the other number? 57.79 minus 1 over 1,000. If this was a test and I was trying to do this quickly because I was running out of time, I'd probably just do 1.57 divided by 57.79 because you'll get about the same answer. Right? 1.57 divided by 57.79 is equal to 0.027. Quality has no units because it's mass over mass. So not a lot of vapor in there, but some. Right? So now that I know this, right, I could find U2 of X2 is equal to UF plus X2 times UG minus UF, right? And now I know X2, so it just goes in over here. I don't actually know VF or UF and UG, but I'm going to look them up on the table, and that will help me find U2. So I want to go down over here and find for, oh, you know what I did wrong? This is a good example of what not to do. I was going too fast because this was for 20 degrees. So I was taking the wrong numbers off the table. Right? So this 57, this would be the state 1 what VG is, but we were supposed to be looking at state 2, and at state 2 we don't know what's going on with the temperature, right? We were only given the pressure, and the pressure was 1 kilopascal, right? So we should have taken our number from here. So our number was in between this and this. So that makes a little more sense. Our quality is a little higher. So you can see that VF here is still about 1 over 1,000. But this should have been 1.67. So let's redo that math. I'm sorry about that. So I looked at the wrong row of the table because I was thinking about the wrong state. So this was, we still conceptually got the right answer, but this number shouldn't have been 57. It should have been 1.67. We're still at 1.57 in between these two numbers. So we still got the phase correct. But our quality is going to be significantly different than this, because this should be, instead of 57 on the denominator, this should be 1.67. So this becomes 1.57 minus 1 divided by 1,000 divided by 1.67 minus 1 divided by 1,000. And we get 94%. I get 938. So we do know the quality, right? But now we want to find UF and UG. And it's important to remember, which is the thing that I just messed up, that here we want to evaluate these properties at state 2. And the thing we know about state 2 is that the pressure is 1 atmosphere, right? Which is equal to 101.3 kilopascals. So now I'm going to go pull UF and UG off that table. Or can I just do this? So the values that I want are UF which is 418.94. In UG, I got to be a little careful. This isn't in the textbook. It doesn't have this middle column, but I want UG and not UFG. This is 2506.5. And this X2, what did we say, was 94, 0.938. So when I put all that into my calculator, I'll do the bracket part first. So I'll keep this 418.94. This is kilojoules per kilogram plus 2506.5 minus 418.94 times 0.938. 1958.13 kilojoules per kilogram. $2377.1. So now I know, if I look at my state table, I know now, I found V1, oops, I don't know why it jumps like that. I must drag my hand wrong around Where did my state table go? Here we go. I found V1 and V2. And actually, because of that, I know V3 because they're the same. I found U1 and U2. So I'm doing a pretty good job with my states. I can figure out the work because here, when I know this, the total work, right? I could either do this as here. So I know that work, I'll do this down here. So I know that work total is equal to the work from 1 to 2 plus the work from 2 to 3. But because the volume didn't change from 2 to 3, I know that that's 0. And because the pressure was constant, we found that this was equal to the pressure at either 1 or 2. It doesn't matter because they're the same. I'll say P1 times, I could write this as V2 minus V1, or I could write this as the mass times P1 is equal to V2 minus V1, little v1 minus little v2. I know that this is 2 kilograms, that the pressure, P1, was equal to 101.3 kilopascals, which is kilonewtons per meter squared. I know my specific volumes, if I remember correctly, was 1.57 for state 2 and about 1 over 1,000 for state 1. Minus 1 over 1,000, which will end up not really mattering. Meters cubed per kilogram. I'm going to check out what's going on with my units first, right? The kilograms cancel with these kilograms. Meters cubed divided by meters squared will just give me meters. I get kilonewton meters here, which is good. That's kilojoules. Right? When I put this in, I'm going to get that work total is equal to 2 times 101.3 times 1.57 minus 1 divided by 1,000 is equal to 317.9 kilojoules. So that's part of the answer that I'm looking for, because that's the total work. I have no gut feeling about the magnitude of this number. So the magnitude of the number, I can't really build any confidence whether or not it's correct. But there's two things that do encourage me about this answer. The first is that it's in units of energy, which is kilojoules, and the sign is correct because my volume was increasing, and because my volume is increasing, I expect the work to be positive, which is what I got. So that's good, right? Now, the rest of the problem, it asked me to find the total heat transfer, right? And we know that that's, that the total heat transfer is equal to Q from 1 to 2 plus Q 2 to 3. Unfortunately, I don't have either of those two numbers, so I got to go back to the first law. Generally, when we're trying to find heat transfer, if it's not given in the problem, we sort of have to use the first law, right? So here, what we can think of is that we already knew, we wrote this out already, that mass times U2 minus U1 was equal to Q from 1 to 2 minus W from 1 to 2. Or that Q from 1 to 2 is equal to the mass times U2 minus U1 plus W from 1 to 2. The good news is here, we fixed state 2 and state 1 already. We know the mass and we know the work. So I can find Q from 1 to 2 is going to be equal to my mass, which is 2 kilograms, times my u, my little u at state 2, which was 2377.1, minus U1, which I expect to be lower because that was for a subcooled liquid. I think we have that up here somewhere. U1 was 83.5 kilojoules per kilogram. Plus my work 1 to 2 is the same as work total. So that's 317.9 kilojoules. Here I get, I'm going to keep these two terms separate. 2377.1 minus 83.5. That's in kilojoules per kilogram. I can cancel my units here. Times 2. This is going to be 4587.2 kilojoules per kilogram plus 317.9 kilojoules. And you can see that I made it, even though I canceled these units out, I messed it up over here. So this is just kilograms, right? Because I took kilojoules per kilogram and multiplied by kilograms. And that's good because, oh no, I don't remember what this number was. Oh, that's 4587. So it's good because I can't add apples to oranges, right? These have to have the same units in order for me to add them together. Right, so this is good. I can do that. Plus 317.9. So Q from 1 to 2 is equal to 4905.1 kilojoules. Again, I don't have a lot of, intuition about what this number should be, but the sign is correct, right? I expect heat in this process, so it should be heat in here. It's a positive number, that's good. And it's in kilojoules, which is also good. Right, so I'm close to being done this problem, right? Because now I have Q1 to 2, but I don't have Q2 to 3. Right, so here again, I can write out the first law, but this time for the second process, that's going to be the mass times U3 minus U2 is equal to Q2 to 3 minus W2 to 3. But we know W2 to 3 is 0. We know the mass. We're trying to find Q2 to 3. We know U2 already. That's this number here is U2. But we don't have U3 yet. So we do have to fix U3. And the things we know about, so when we looked, if we went up to our state table, right? So at state 3, our pressure is equal to 4 bar. And our specific volume is the same as V2, which is 1.57 meters cubed per kilogram. So I have two independent intensive properties, which is what I need to fix a state. But again, I ask myself, what's the fluid? Again, it's water. Now I got to ask myself, is this two-phase? Or is it superheated? And I don't know. So I know the specific volume. So what I can do is two things. So here, because I have only so many tables, right? But one of the tables I have is for superheated water vapor. And I have 4.4 megapascals, which is 400 kilopascals, which is 4 bar. So this is the right pressure. Usually I'm used to now, what if I know the temperature, then I can go through and fix the states. But I don't have that here. Instead, I have the specific volumes. And my specific volume is 1.57, which is in between these two numbers. So I got to find for state 3, my interpolation factor A is going to be my specific volume at 3 minus V min divided by V max minus V min. So this is 1.57 minus the lower number here. I'm just going to call it 1.47 divided by 1.584 minus 1.47. So I'm going to expect this to be a pretty high number, right? Because I'm a lot closer to 1.58 than I am to 1.47. So I got 1.57 minus 1.47 divided by 1.584 minus 1.47. And the answer that I got was 0.88. But A is also going to be equal to U3 minus U min divided by U max over U min. Right? So now I got to look for these specific internal energy numbers over here. I don't know this value for U3. The nice thing about doing it this way, though, is I get basically the same as my quality equation, that U3 is going to be equal to U min plus my interpolation factor A times U max minus U min. Or that it's going to be equal to 4052, these are all in kilojoules per kilogram, plus 0.88 times 4256.5 minus 40.52, or so for this is, there's no decimal there, that's just 4052, sorry. And my answer is going to be 4256.5 minus 4052 times 0.88 plus 4052. I get 4231.96 kilojoules per kilogram. That's good because it's in between these two numbers. Right? And it's closer to the higher number, which I think it should be. So now I can put this finally up into this equation over here. This is equal to my mass, which is 2 kilograms, multiplied by U3, which was 4231.96, minus U2, 2377.1 kilojoules per kilogram is equal to Q23 minus 2377.1 times 2. So here I get that Q2 to 3 is equal to 3709.72. My kilograms cancel, so this is just kilojoules. Again, I'm not sure if the numerical value is correct, but I like that my sign is correct because it told me I was adding heat for both of these two processes, and I like that the units are correct. So when we look at this whole process, we can add these two heat transfer values together to get Q total. It's equal to 4905.1, 86, 14.82 kilojoules. What did I do? That's 82, right? So again, I don't know that because I don't work in this industry or whatever, like I don't know if the number makes sense. but the sign is right and the units are right, which means that I can't prove that my answer is wrong. Right? And that's pretty good. That's something. Right? So I feel pretty good about this answer. If I was going back up here, so I think we answered everything in the problem. But we didn't finish drawing these diagrams. So remember, our state 3 ended up being over here. Right? So this was, we went state 1, state 2 was under the vapor dome, and then state 3 ended up being over here as a superheated vapor. So we had to, when we added heat, we increased the pressure, right? So our pressure became 4 bars. Well, I guess I sort of drew this incorrectly, but our pressure became 4 bars, and we ended up in this superheated vapor region. Right? If we were drawing it down here on our TV diagram, we went from state 1 to state 2 over here. State 2 wasn't a two-phase mixture, so that part of the graph we weren't sure about. And then when we added heat from state 2 to state 3, we ended up being over here as a superheated vapor. Whenever you draw these sketches, especially because we often ask them early in the problem, I'm not super concerned if in this case, because we didn't know where state 2 ended up being, if you drew state 2 over here on a test, but still had, state 3 vertically above state 2, you'd still get the points, right? Because we didn't exactly know where this was, right? And if I asked you before you could actually figure it out, then I won't penalize you if you put it not quite in the right place, right? But ultimately here what we did was we said it was a closed system. We used some assumptions to get to the mass times the change in specific internal energy, right? And then we used the PV relationships in both of these two processes to find the work. And then we had to ask ourselves, well, we know it's water, but what's the phase? And we got a chance to use all 3 phases in this particular case. And we fixed the states. And because of that, we could find the change in the specific internal energies. And then with that, we could find the heat transfer. So this is what you might see on an exam. Now, this one maybe is a little bit long to be an actual exam problem, right? But if you could do this problem, then you would be ready to do the exam. Because I could maybe give you a little bit more information than this. But, you don't know if you can do all of these parts, then whatever I ask you on an exam, you're good for when the fluid is water. Does anybody have questions about this example? All right, so I know we spent some time with this one. We'll come back maybe at 7:48, and we'll do another example that's still a closed system, but it's going to be an ideal gas problem. And we might do 2 of those, and then I don't know how much open system stuff we'll get to. But our next problem will be open system or closed system with gas. So I will see you in 5 minutes or so. Okay, welcome back, everybody. We're going to just jump right into the next problem. So this is another first law problem. It's another closed system problem. But here, the difference is going to be when we ask ourselves, what's the fluid? It's going to be an ideal gas instead of water. So it's a little different, right? So we know some information about state 1. We've got pressure, volume, and mass. We know the pressure at state 2, and we know this pressure-volume relationship. We're also given the specific gas constant for air. We would like to know, as we move between these 2 states, what's the work and what's the heat transfer in the system, right? It says heat transfer to the system, work performed by the system. So one of these things, at least right now, we can tell what the sign's going to be. Right? So in this case, our area is expanding, right? As we go from state 1 to state 2, the volume is getting bigger. What that means is that the work we expect to be positive. So here I'm expecting work to be positive. Q, I don't really know, right? But that's why I have the first law, right? So I'm going to say that my first assumption, so assumption 1, is going to be that this is a closed system. And because it's a closed system, that means E2, well, I'm just going to write the whole thing, right? So that means we're going to say that the change in kinetic energy plus the change in potential energy plus the change in any spring energy in the problem plus U2 minus U1 is equal to Q minus W. I'm going to assume that the kinetic, potential, and spring energies are all negligible. That doesn't necessarily mean that they're zero. What it means is that the changes in these things we're assuming are much smaller than the change in the internal energy. Right? So I can neglect these things. They might as well be zero. Right? It's like a speck of sand to a beach. You know? And then this means that the mass times little u2 minus little u1 is going to be equal to Q minus W. This is a good situation to be in, and this, for every long answer problem, it always breaks my heart a little bit on an exam if somebody submits something and it's totally blank. For any long answer problem on the first exam, you can write this. I assume it's a closed system. That means I get this version of the first law. Probably I can neglect these three things, but look at the problem. If it tells you something about kinetic energy change, don't neglect it. Then you get to here, right? And now we're at the point where I'm going to try to find work as the integral of P dV. And I need to fix this. So here I need to know what's the fluid. In this case, it's an ideal gas. And when it's an ideal gas, instead of asking what's the phase, I got to say, is it constant specific heat or variable specific heat? I'm going to do this part second. I'm going to try to do it both ways, right? And then you can see how to do it both ways, right? But first, so here, right, this is my equation 1. First, I want to find the work, right? So here I know that work from 1 to 2 is equal to the integral from state 1 to state 2 of P dV. But I was told that pressure times volume to the 1.5 is constant. I think it was 1.5. Yes, PV to the 1.5 was constant. That means that P as a function of V is equal to constant over V to the 1.5, or as I prefer to write this, CV to the negative 1.5. This is pretty similar to an example we did in class, but honestly, that was last week, and I know we're sort of drinking from the fire hose. So instead of just going right to the answer, you might already have some idea what the shape of this answer is going to look like, but it's okay if you don't, because the process of getting the answer is always going to be the same. So if you don't remember what the answer should look like, you can just do the math, right? So this is going to be the integral from 1 to 2 of this constant times volume to the negative 1.5 dV. But I can take the constant out, integral from 1 to 2, V to the negative 1.5, dV. This is a case where you actually have to do some calculus, which for me, again, always a little nervous, right? So here I go C, but what happens is I add 1 to the exponent, so I get V to the negative 0.5, and then I divide by what I have left up here, negative 0.5, and I'm going to evaluate this from 1 to 2, or this is going to be, well, let's do it over here first, C times V2 to the negative 0.5 minus V1 to the negative 0.5 divided by negative 0.5. I prefer not to have the negative sign in the denominator because I'm weird, right? So I'm going to multiply the numerator and the denominator by negative 1, right? Negative 1 over negative 1 is 1, so I'm allowed to do that, right? This is going to be C times V1 to the negative 0.5 minus V2 to the negative 0.5 divided by 0.5. But now I remember, right, that this constant, this is true at state 1 and state 2. If P1 to the 1.5 is true everywhere on this line, that means it's true at state 1 and it's true at state 2. So this constant, it can be P1 V1 to the 1.5, but it could also be P2 V2 to the 1.5, right? So when I multiply this by state 1, I'm going to call it P1 V1 to the 1.5. And when I multiply it by state 2, I'm going to call it P2 V2 to the 1.5. Right? So this is going to be, and I won't skip the step, right? So this is going to be P1 V1 to the 1.5 times V1 to the negative 0.5 minus P2. Pardon me?
I think you switched V2 and V1 around.
I did when I went from here to here because I multiplied by negative.
Right.
Yep. Yep. So I could have left it as V2 minus V1 if I left the denominator as negative 0.5. So P2 V2 to the 1.5 multiplied by V2 to the negative 0.5. But I certainly will make mistakes in problems. So if you ever think that I'm making a mistake, please let me know. Because then we can figure out what I'm doing wrong as I'm doing it. So I appreciate that. Divided by 0.5, right? But here I just add the exponents. So this is going to be the general solution when n is not equal to 1 is P1 V1 minus P2 V2 over, this is n minus 1, right? Because remember our n was 1.5. And this will be true as long as v is not equal to 1. If v is equal to 1, you get that natural log thing going on. Right? So this is going to be my work from state 1 to state 2. So now I want to go back up here to my state table. Let's see if I can make this smaller and copy it down. Let me. I don't know, did it paste it somewhere and I just didn't see it? Here we go. Well, anyway, I know that my P1 is 80 psi and my V1 is 0.1 feet squared, right? And the beauty of this method so far is that this is an imperial problem, which I tend not to like as much. And now for some reason my pen doesn't work. Oh, here we go. But the symbolic part, it doesn't matter until we start putting numbers in, right? So here I know that P1, well, if I write out my state table, right? So I have my states 1 and 2. P1, V1, T1, or PV and T. Right, so pressure is in PSI, volume is in cubic feet, and temperature should be in Rankine. We'll see what they gave it to us as. So for state 1, 80 psi and 0.1, this should be cubic feet. State 2, they only told us the pressure, 14.7, which is atmospheric pressure. Now, in order to do this, I need, so if I look at this, right, if I look at my work equation, here I know P1, I know P2, I know V1, I don't know V2. This N is 1.5 minus, so this I know, right? But I don't know V2. So I need to think about what I know in order to find V2. And in this case, there's a couple of things. I got a couple of choices, right? So it's an ideal gas problem. So I could always use the ideal gas law, right? But I can also use this equation here because I know between my two states, this is constant, right? So I'm trying to find V2. So if I get V2 to the 1.5 is equal to P1 over P2 multiplied by V1 to the 1.5. Right, so here if I work this out, P1 over P2, 80 divided by 14.7 is 5.44. That doesn't have any units. This is the nice thing about an equation like this, is because the units are canceling out. So even though that this is in PSI and this is in cubic feet, right now that doesn't matter. It will matter in the future, but for right now it doesn't matter because P over P is dimensionless, right? As long as those are both absolute pressures. Now this is going to be 0.1 feet cubed to the 1.5, right? But then to get to V2, right? So if I don't want V2 here, then I have to do this over 1 over 1.5 as my exponent here. And that'll let me just have an expression for V2. So 0.1 to the power of 1.5 times 5.44 all to the power of 1 divided by 1.5. And I get 0.31 cubic feet. So now this I know, okay? So I can put this into my equation, right? Now is when I have to start worrying about units. So this is going to be P1, which is 80 pounds force per inch squared, times 0.1 feet cubed minus 14.7 pounds force per inch squared times 0.31 feet cubed divided by 0.5. So here, first I'm just going to work it out numerically, and then I'm going to worry about the units after. So the good news is both of these terms are in the same units. So I can subtract them, even though it gives me kind of a weird unit. Right? So it's going to be 80 times 0.1 minus 14.7 times 0.31 divided by 0.5. So I'm going to get an answer here of 6.6 6.89. But it's going to have these weird units of pounds force per inch squared times cubic feet. So what I want my work in is foot-pounds. Foot-pounds is a unit of work because it's force times distance, right? So I'm going to multiply this by, I want to get rid of my inches squared. So there are 12 squared inches squared per foot squared. So that means my inches squared are going to cancel out. Cubic feet divided by square feet is going to give me just feet. So I'm going to have foot-pounds on top. My answer is going to be significantly bigger than 6.89 because I got to multiply this by 12 squared, or 144. And I'm going to get 991.6 foot-pounds force as my work from 1 to 2. So again, I don't know numerically if the number here is right, but I feel good that the units are in units of energy, force times distance, and that because my volume was increasing, I got a positive value for work. Right? So I feel pretty good about that process. Even if it ended up getting me the wrong answer on a test, I followed a good process, right? And I'm at least mostly correct. Right? I think I'm actually correct, but I'm at least mostly correct. Right? Let's get some more space down here. So now comes the point where we got to deal with that left-hand side of our equation, because remember, we were saying that the mass times U2 minus U1 is equal to Q minus W, right? The good news is now we know the work. I think they told us the mass, but I don't know U2 or U1. Instead of doing it both ways, because we're going to do two ideal gas problems, why don't I pick one here? So I'm going to do this one as, so now here I got to ask what's the fluid. Right, here it's an ideal gas, air. So it has to be in variable specific heat or constant specific heat. We're going to do two different problems in two different ways here. On an exam, I will tell you which method I want you to use. It's always best to pick the method that I ask you to use, but the next best thing is to use the other method. Right? The worst thing to do is leave it blank. Right? So if I ask you to do variable specific heat, but you don't remember how to do variable specific heat, well then do constant specific heat, because that's a lot better than doing nothing. Right? Here we're going to do constant specific heat. So under the assumption of constant specific heat, we're never going to find the individual specific internal energies. Instead, we're going to take the mass times CV. Actually, you know what? I think here, because they don't tell us what CV is, I'm going to change my mind. I'm going to do this one as variable specific heat and the other one as constant specific heat. So here we're going to do variable specific heat and not constant. This is the more accurate answer, right? The downside is we got to use the tables, right? So here this is going to say we need to find U2, which is a function of T2, using table A22E. Right? And we also have to find U1, which is a function of T1 on table A22E. The downside of this is that I don't know T1 or T2. When you get into a situation and you're using ideal gases and you can't find one of pressure, volume, or temperature, that's a good bet, or mass, that's a good bet that you're going to have to use the ideal gas law. So here we'll use the ideal gas law, which we know is pressure times volume is equal to the mass times R times T. Because this is not a delta T, this is going to give us temperature in absolute temperature, right? In this case, because it's an imperial problem, it's going to tell us the temperature in Rankine. Rankine is like Kelvin, but for the imperial system. I'm going to start here at state 1, because even though I calculated volume 2, I have more confidence in the value they gave me than in the value that I calculated. Because maybe I put something wrong into my calculator, right? But from here, I can find T is equal to PV over MR, right? And because I'm looking for T1 first, P1 V1 over MR. Now, I got to go back up because they told me the value of R, 53.35 foot-pounds force per pound mass Rankine. So I know that my pressure at state 1 is 80 psi. Well, instead of writing psi, just like before, I'm going to write this as pounds force per inch squared times my volume is 0.1 cubic feet divided by my mass. Is it 0.01? I can't remember. 0.01 pounds mass. Times R, which we transpose down here as 53.35 foot-pounds force per pound mass. Now the good news here is that the pounds mass cancel, but we don't have foot-pounds on the top, right? We got cubic feet times pound force over inches squared. So again, we're going to have to get rid of that inches squared as 12 squared inches squared per foot squared. The inches squared are going to cancel. That's going to cancel. And now we have foot-pounds. Foot-pounds canceled with foot-pounds. And we're going to get, oops, there should be a pounds mass degrees Rankine over here. And then our denominator is going to be 1 over Rankine, which is Rankine, right? So here, if I put all of this junk into my calculator, I'm going to get 80 times 0.1 divided by 0.01, that's 800, divided by 53.35, so that's 14.995, 1 over 1. Oh no, because I forgot to multiply by. See, and this is the thing where intuition can help you. Because here, right, because I didn't multiply by the 12 squared, I forgot in my calculator. But like, remember this absolute temperature, right? So 14 degrees Fahrenheit above temperature, above absolute zero is really cold, right? So here I got to take that 14.99 multiplied by 12 squared, because I'm doing that, I'm like, that doesn't really look right, right? And instead of that, we get 2159.3, and this is 1 over Rankine, right? But that's just Rankine. 2159.3 Rankine. So now we know that T1 is equal to 2159.3 Rankine. And sometimes you have to use the ideal gas law like that. And it's a pain because the units are a pain. But the neat thing is, once you know one of your states, and you know PV and T, and you only need one thing at the other state, then you're in a pretty good position. Because we can see when we write the ideal gas law out, right? We know that PV is equal to M. I don't know why it does that. Sorry, I'm lost on the page here. PV is equal to M R T. But because this is a closed system with no chemical reactions, the mass stays constant because it's closed, and this specific gas constant stays the same as long as it's the same gas. So if there's no chemical reactions, it's the same gas, and what that means is that PV over T is equal to MR, and that's true at state 1. It's also true at state 2. So I don't care about M and R anymore because they're constant. Right now, what I'd like to find from this equation is T2, right? So when we look at this, I know P1 and V1 and T1 and P2 and V2, but I don't know T2. So if I'm trying to find T2, that's going to be equal to T1, and then I'm going to get a couple of different ratios, right? So T1 times P2 over P1 times V2 over V1. And there's some beauty in this because these pressures are both in PSI, but it's a ratio of pressures in PSI. So this pressure over pressure has no units, and these volumes are in cubic feet, but it's cubic feet over cubic feet. So those units disappear too, and I get one temperature in Rankine is equal to some other temperature in Rankine. So I can take T1, which I know is 2159.3 Rankine, times V2 when I calculated it. Up here was 0.31 feet, so 0.31. Oh, I guess I do the pressures first. 0.31 over 0.1. Those are cubic feet, but they go away, right? And these pressures are in PSI. P2 is 14.7 and P1 is 80. So I'm going to get 2159.3 times this 14.7 divided by 80. This is 0.18, and this is about 3. .31. So then this is times 0.18 times 2159.3. This is going to be 1204.9 Rankine. This is T2, and T1 was equal to 2159.3. And this is great because I know that these specific volumes or the specific internal energies are a function of the temperatures. But I'm not done yet, right? Because I need to actually find those values on the table. Here, why don't I do this? So and they're not on this table. Oh, that's unfortunate. But if they were on the table, right, then what I would do is I would find the values in between. Right? So here I would go to, let's pull up. What would we say, 2159 or something? And what are the values? 2159 and 1204. 2150. Oh, it's in between that. Okay, so I'm going to snip this. So some of this stuff, we don't know what it is yet on this table, but we know this is temperature in Rankine. This is U. No, this is H in kilojoules per kilogram. This is U in kilojoules per kilogram. And the rest of this stuff, we don't know what it is yet. So my two temperatures are 1204.9, which is 1205, and 2159. 1205 and 2159. So I didn't go. Sorry. So 2159, right, is just above here. Let me go back and get a better snip here. So here, 1205 is in between $1,200 and $1,240. So I need to find my interpolation factor. A is going to be 1205 minus 1,200 divided by 1,240 minus 1,200. 1205 minus 1,200 divided by 40. That's 0.125. Oh, yes, you're right. It's not kilojoules per kilogram. That's a great point because we're in a different unit system. So these are in BTU per pound mass. So it's still energy per unit mass, but because it's imperial, it's in BTU per pound mass instead of kilojoules per kilogram. Thank you. So now my U value is going to be the minimum value here. 209.05. No, it's going to be the value that I want. U1 minus U-min, which is 209.05, divided by the maximum value, 216.53 minus 209.05. But I want to rearrange this, right, because I don't know U1 and I do know A. So this is going to be U1 is equal to U min, which is 209.05, plus 0.125 times 216.53 minus 209.05. And I'm going to get 235.2 and correctly BTU per pound mass. So that gives me U1, which is good because now when I go back to my first law, now I know U1. The only thing here I don't know is U2. Unfortunately, it means I got to interpolate onto the next row of the table. So if I come down over here and I snip just this guy, sometimes I'm just going to leave it like this, maybe. We'll see. Yep. So now this is my U value here. And this is my other U value. So here you can see in this 50 degrees, it goes up about 10, right? So we have my interpolation factor B is going to be similarly, right? So we know the temperature, our other temperature is 1205. No, this one is the 2159 minus 2150 divided by, this is now the full range, 2200 minus 2150. And this is going to be 9 divided by 50. .18. When I try to find U2, it's going to be the minimum value, which is 399.17, plus my interpolation factor B, 0.18, times the big number, 409.78, minus 399.17. 409.78 minus 399.17 times 0.18 plus 399.17 is equal to 401.07 BTU per pound mass. So now I have U1 and U2. So my equation, which was mass times U2 minus U1, is equal to Q minus W, or Q, which is now the thing I'm looking for, is equal to M times U2 minus U1 plus W. I know all of these things. The mass, I believe, what was it, 0.01 pound mass? I think. .01 pound mass times U2 is 401.07 minus 235.2. This is in BTU per pound mass, which is nice because those two things cancel. Oh, and now we're going to get a problem here. Because when I calculated the work I did in foot-pounds, it's 991.6 foot-pounds. Now, this is a thing that you're probably going to eventually kind of have burned into your head, even if you don't want to. But here, let's see if we can find it. Is it here? If not, it's on the equation sheet. Energy. So 1 BTU is equal to about 778 foot-pounds. So that's, if you're looking for it in this reference table, which is on the website on the very first page, or I've also put together an equation sheet for the class and it's on there as well, right? So here I know that 1 BTU is equal to 778 foot-pounds force. So when we add these together, it might look like one's really small and one's really big, right? But we don't really know anything until we get everything into the same units, right? So 401.07 minus 235.2 times 0.01. So this is 1.66 BTU plus 991.6 foot-pounds force times 1 BTU per 778 foot-pounds force. So those cancel, right? So now this one that looked like a really big number, it's actually not that big, right? Or at least it's of the same magnitude as this number, right? So this is 1.66 plus 981.6 divided by 778, and we get a total of 2.93 BTU. Or you could convert that to foot-pounds if you wanted to. So you could multiply the whole thing by 778. So that's Q. So hopefully we're starting to see that most of these first law problems are kind of similar, right? That's the second problem. Did anybody have questions about here? So the difference here, even though we followed the same general process, is when we got to the question, what's the fluid? We had to start looking at what do we do with ideal gases. And this time we used the variable specific heat method. So we had to find the temperatures and go to table A22, or in this case A22E, to find our specific internal energies. That kind of makes sense? Okay, let's take 5 and we'll come back at 8:38 and we'll go through another example. I don't know how much open system stuff we'll start to work on, but we do have a little slack in the course outline, so it'll be okay if we're a bit behind. I think it's good to go through these kind of problems because they're the kind of problems you're going to see on the exam. All right, welcome back, everybody. We'll try to dig into this third example problem. I think this one in some ways is the most complicated, but if you could do this one, I think you'd be in good stead for the exam. So here we have a picture of a piston cylinder assembly, and the weird thing is we have this paddle wheel that's putting work into the system. So it says that a piston cylinder assembly is fitted with a paddle wheel, and it contains air, initially at some pressure, temperature, and volume. The air undergoes a process to some final state where the pressure is different, lower, but the volume is higher. During the process, the paddle wheel transfers. So here we have the paddle wheel that's putting in, sorry about the highlighting. Let's see if we can get rid of that. So the paddle wheel here is putting in 1 BTU, while the air transfers energy to the piston. So the air is pushing the piston out at 3.31 BTU. Assuming ideal gas behavior, determine for the air the temperature at state 2 in degrees Rankine and the heat transfer. So here we're going to assume, so first it tells us it's an ideal gas, so we can assume that it's an ideal gas in a closed system. So this means that we get delta E is equal to Q minus W, but here I'm going to assume that the change in the kinetic energy is approximately equal to the change in the potential energy, which is approximately equal to the change in the spring energy, approximately equal to 0. So my first law, unsurprisingly, right, is going to become M times U2 minus U1 is equal to Q minus W. We're trying to solve for, well, I'm going to say W net over here. We're trying to solve for Q. Q is equal to M times U2 minus U1 plus W net. Usually, what I would tell you, right, what we've been saying this whole time is work is equal to the integral of P dV. But in this case, we cannot use this relationship because we don't have a pressure-volume relationship. Instead, they just told us, so this is going to be the work from the paddle wheel plus the work from the system. And here, whenever we do this, right, we have to be weary when they give us numbers. Anytime a textbook problem gives you numbers like this, you know, the hair on the back of your neck's got to stand up a little bit, just like heat transfer, because this isn't just a number, it's a number and a sign, right? So for the paddle wheel work, we're putting work into the system. So what should the sign for this be? Remember, we know that heat in is positive and work in is negative. So I think we had a question, I don't know, a little while ago where it was like, is it good to draw or do you have to draw these schematics? And you don't always have to, right? Although if a problem specifically asks you to, you should, right? But when you draw them, it's nice because here I can see that work is coming in from the paddle wheel. So work in, so this is negative, right? But work is going out because it says it's from transfers air transfers energy by work to the piston. So the air is pushing out here. So that work in is negative, work out must be positive, right? So this is really plus minus, the paddle wheel is 1 BTU, plus 3.31 BTU. So it's a little tricky here because we had this, right? So the work here is actually easier. There's no calculus or anything, but we do have to think about the signs of the works, right? Now, anytime that I have delta U, I got to think, what's the fluid? In this case, it's an ideal gas. And because it's an ideal gas, I have to say, is it constant specific heat or is it variable specific heat? Last time we used variable specific heat, so this time we're going to use constant specific heat. If it's constant specific heat, what happens is delta U becomes CV times delta T. right? So that's the difference, right? And this is great because now this equation, right, or U2 minus U1 becomes CV times T2 minus T1. The problem, I think, tells me CV, although I gave you the opportunity, I told you CV and CP in this problem, giving you the opportunity to demonstrate that you understand which one you're supposed to use when you have delta U, right? So I know CV and I know T1, sort of. I know CV and I know T1. Now, here, they're kind of being sneaky because they told me the temperature, but they told it to me in Fahrenheit. I don't care about Fahrenheit temperatures for ideal gas problems. I always want to turn these relative temperatures into absolute temperatures. So I want to turn this into Rankine, right? And here the problem told us that if we have a Fahrenheit temperature, right, then we have to add 460 to get to a Rankine temperature. So 540 plus 460 is 1,000 Rankine. So here they told me the Fahrenheit temperature, which seemed like a nice thing, but always turn ideal gas temperatures into absolute temperatures. Either Rankine if it's imperial like this, or into Kelvin if it's metric. The other nice thing about doing it as constant specific heat is I don't care what the value of U is, because I'm never going to find the individual values of U. Instead, I have an estimate for what delta U is. So this would be good, and I would be finished this problem already if I knew T2. But I don't know T2. So I got to use something to find T2. And when I have an ideal gas law problem, and I'm sitting around thinking, man, I wish I could fix the state, but I don't know what the temperature is, or the volume is, or the mass is, I can remember to use the ideal gas law. In one of two ways, I can say that PV is equal to MR times T, or I can remember that because it's a closed system with no chemical reactions, then the mass stays constant because it's a closed system, and R is constant because the gas doesn't change. So then I prefer to use the ideal gas law this way if I can. So PV over T is equal to MR, but since M and R don't change, that's constant. P1 V1 over T1 has got to be equal to P2 V2 over T2. Right? The thing that I'm trying to find is T2. So here I'm going to say that T2 is equal to T1 times P2 over P1 times V2 over V1. And I'm going to hope I have the rest of that information. So P2 over P1 is 2 over 3. So this is 1,000 Rankine times, this was 20 psi over 30 psi. But the psi's cancel. So as long as they're both in absolute pressures, that's fine. V2, oh, and they gave me V2 and V1, 4.5 divided by 4. These are both feet squared, or feet cubed, I'm sorry. They cancel. So here I'm going to have 2 divided by 3 times 4.5 divided by 4 times 1,000, and I get 750 degrees Rankine. Now, if we were going to use variable specific heat, then I would take 1,000 degrees and 750 degrees, and I would go to table A22 and I'd look it up. But I don't have to do any of that stuff here because I just put it in here, right? So now U2 minus U1 is equal to CV, which they told me, 0.208. This is in BTU per pound mass degree Rankine times T2 minus T1, or I guess I can put the numbers in, which is 750 minus 1,000. That's going to be 750 minus 1,000 times 0.208. Negative 52 BTU per pound mass. But did they tell me the mass? I don't think they did, right? So when I look here, right, so I can see that I need Q is what I'm trying to find. Mass times U2 minus U1. Or because we use constant specific heat, this became CV times T2 minus T1. And anytime you do that, you have to tell me you're using constant specific heat. That's your assumption. Plus the work. Good news is I know CV, I know T1, I know T2, I know the work. I don't know the mass. This is my preference for using the ideal gas law. But here we ran into a snag because I need to find the mass. And usually if you have an ideal gas law problem and you need to find the mass, the way you do it is you know that PV is equal to MRT. You go to the state that you know the most about. That's probably state 1. And I say that M is equal to, M is the same. So you could use state 1 or you could use state 2. But I'm going to say P1 V1 over R T1. Unfortunately, in this problem, they don't tell me R. So I'm going to show you how to find it or how to calculate it. So R is equal to R bar divided by the molar mass. R bar, if we go on to our, again, the first page on our reference sheets, the universal gas constant is here, and it's here in a couple of different units, right? So if it's metric, right, then I'm going to use this 8.314 kilojoules per kilomole Kelvin, right? But here, I want the BTU version, 1.986 BTU per pound mole degree Rankine. So that's 1.986 BTU per pound mole degree Rankine. Now I want to find the molar mass. Molar masses can be found on table A1 or A1E if you're in imperial or English units. So atomic or molecular weights are the same as molar masses, right? So here I'm going to go to table A1. I'm looking for air, and my, oh, this is right at the beginning. So I want to find, that's table A1, but I want table A1E. You'll notice the coloring changes. For the metric tables, they have this like nice light orange highlighting. But once we get into the imperial tables or the English tables, it starts to be this grayish or blue or whatever you want to call that. So for air, it's 28.97 pounds mass per pound mole. 28.97. Since I have pounds mole in the denominator of the numerator and the denominator of the denominator, they cancel out. And I get, 0.986 divided by 28.97. You're at 0.0685 BTU per pound mass Rankine. Right, so pressure 1 was 30 psi. Pounds force per inch squared times the volume, I think, was 4 cubic feet. And again, you have this thing. So this is a pretty common thing, right? 4 feet cubed is that you've got this pressure in inches squared, per inches squared, and you've got volumes in cubic feet. Right? Now you got this 0.06, we're going to call it 9 BTU per pound mass Rankine. And our temperature, T1, was 1,000 Rankine. Right, so now first I'm going to check the units, right? And I see that I got this problem, this unit mismatch. So I need 12 squared inches squared per foot squared. Right, now I've got foot pounds here, which is another unit mismatch. So maybe I could have picked the other version of R here. But I also want to take this foot pounds and I want to say that times the numerator times I want 1 BTU on the top per 778 foot pounds force. Right? And now my foot pounds are going to cancel there, and I got BTU on the top. The BTU is going to cancel with this. The Rankine's going to cancel with this. And the units I'm going to get are 1 over 1 over Rankine, which is good because that's or 1 over pounds mass, which is good because that's pounds mass, which is what I want. All right, so this is going to be 30 times 4 times 12 squared divided by 778 divided by 0.069 divided by 1,000, and I get my mass is 0.32 pound mass. So finally, now I have this, right? And I can put all this together into my equation, and I get that this is 0.32 pound mass times CV, which was, I know that this is negative 52 BTU per pound mass. Those cancel. So I'm going to get BTU as my first term plus my work, which was on net 2.31 BTU. And my Q is going to be 0.32 times 52, but this is negative 16.6 4 plus 2.31. This is all in BTU. And my final answer, plus 2.31, is going to be negative 14.3 BTU. Now, after you do all of this on a test, it will normally ask, comment on the direction of the heat transfer. All right, so here you say, this is negative. Q is less than 0, right? I know that heat in is positive, so this must be heat out. All right, so if I was drawing this over here, I drew my two work terms, but now I'm going to draw my heat transfer term, and that's leaving the system. I don't automatically get a sense of what the right sign is for the heat transfer. But I do have some confidence here because at least I got the right units. I didn't get something funny like BTU plus foot-pounds force or something, right? So at least I know that the units feel good. I didn't prove that my answer was wrong that way. So I have some confidence in this number, right? But I don't know in total if it should be positive or negative. I don't have intuition about what that should be. But I do feel pretty good because at least I got the right units. And again, we followed the same general process where we made the assumption that it was a closed system, right? If we go to this, right? So we made the assumption that it was a closed system. So we had E2 minus E1 is equal to heat minus work. We found the work, although in this case, it's a little different because they told us the work in two separate parts. So we had to think about the sign. And then we fixed our states, right? So here we fixed our states when we went through our flow chart. We said, oh, it's an ideal gas. And we used constant specific heat. So delta, the change in little u became CV times the change in temperature. And that's it. I know it takes longer than, the 2-minute explanation there. But that's the general process. And all of these closed system energy balance problems are like that. So if you can sort of follow that general process, then I think you'll be in a good state for the first midterm. So we will take a short break here, come back at 9:05, and then we'll sort of introduce the idea of conservation of mass, and that because that's the first question that we have when we start to look at open systems. So I'll be back in 4 minutes or so. Okay, thanks everybody. We're in the home stretch now. I appreciate you sticking with me. I know going through the examples, I think it's valuable, but I know especially when we do, 3 hours or 2.5 hours of examples straight like that it, it can probably take a significant amount of concentration to try to follow it. But hopefully you sort of get this general idea that when we have a closed system, which is what the long answer problems for the first midterm will be, we have delta E is equal to Q minus W. Then we'll make some assumptions, and we'll get to the change in the specific, or the change in the internal energy is equal to the heat transfer minus the work. We'll find the work as the integral of PDV, unless they just give it to us. And then we'll need to fix the states to find the change in the specific internal energy. To do that, we need to know what the fluid is. If it's water, we'll want to know what the phase is. Is it a subcooled liquid, a two-phase mixture, or a superheated vapor? And if it's an ideal gas, we're going to want to know if we're going to use constant specific heat or variable specific heat. That's generally what we do if it's a closed system. But now we got to start increasing the complexity of the processes we're going to look at. So what happens when it's an open system? And the first question we want to know is what happens to the mass? This was a trivial question for a closed system because the answer to what happens to the mass for a closed system is always it just stays in the system. So nothing happens to the mass. But for open systems, mass is coming in and out through different ports in our system. So if you think about something like an internal combustion engine, there's air coming in through the air intake, right? There's exhaust gas coming out. There's fuel coming in, right, through the fuel injection, right? So there's mass that's always coming in and out of the system. So not only can you have heat transfer and work going on, but there's mass coming in and out. And one of the things that we've hopefully seen over the last week and a half is that mass carries energy with it based on its temperature and its pressure. So in order to do an energy balance, in order to figure out how energy is conserved in a system like this, where mass is moving in and out, we need to know what's happening with the mass, because the mass is carrying energy with it. So generally for open systems, there's at least 3 questions that we want to answer. The first is, where do we draw our control volume? that's kind of like, where's the boundary between our system and the surroundings? Or what part of the universe are we most interested in? Right? And then the second question is, what happens to the mass? And that's what we're going to start to look at here at the end of this lecture. And then only after we figure out what's going on with the mass, how is it coming in and going out, then we'll be able to answer what happens to the energy. Right? Because we need to account for what's going on with mass coming in and out before we can get a full accounting of all the energy coming in and out of the system. So we're going to talk today about this idea of conservation of mass. Sometimes, because we just love these engineering decoder ring words, instead of calling it conservation of mass, sometimes we just call it continuity. I don't exactly know why. Right? What this means is that the change of mass in the system over some time interval is equal to the net inflows of mass minus the net outflows, right? And that's pretty straightforward if you think about a cup of water, right? So, there's some amount of water in my cup, but if I turned it over and poured half the water out, then I'd only have half of the amount of water left, right? Or if I put it out in the rain, right, and I collected an extra 20 grams of water, then the mass in the cup would go up, right? So that's this idea of conservation of mass, right? So there's the change in the mass in the system, which is like the change in energy that we've been talking about, right? Over time, in this case. And if I want to find that change in mass over time, I can add up all the mass that I put in and subtract all the mass that I take out, right? Like, you didn't have to go to university to figure that out, right? So that's what the net inflow of mass is, right? So here's a picture of maybe some ductwork or something, right? And if we think about conservation of mass, right, first we draw our control volume. So what I do with the control volume is, if there's a solid wall in my system, I draw a boundary of my control volume there, right? And if there's a port where mass is coming in or out, I draw my control volume so that it's 90 degrees to the inlet or 90 degrees to the outlet. It doesn't matter too much in this class, but as you start to move on to fluids and you do some vector calculus across this boundary, it helps if the fluid is going 90 degrees to the boundary of your control volume. But we won't do that kind of calculus in this class, right? Just in the class Rejoice, right? So if I have some initial amount of mass in my system, and I want to find the final mass, right? Then I can count the inflows and the outflows, right? One thing I could do is I could block up the outlets and I could add mass, right? And if that happened, then this mass at the outlet would go to zero, right? I'd only be adding mass. So that must mean, right? So the right-hand side of my equation would be positive, which means the left-hand side of my equation must be positive. So M2 must be bigger than M1. Right? And this is not to show you how math works, right? This is to try to build your confidence in the idea of this equation. So it kind of makes sense, right? But if I have some water in my cup, right, and I pour some out, now I have less water in my cup, right? So if there's no mass coming in, but there is mass going out, then that means the right-hand side of my equation is negative. So the left-hand side of my equation must also be negative, or M2 is less than M1. Right? So this is a diagram, it's kind of crude, of what conservation of mass looks like. At least in this elapsed time world that we've been using for closed systems. Right? And maybe that's a hint of what's to come. Right? Now, there's this kind of special case that we talk about, right? Because right now, the amount of water in my cup is not changing. But that's just because nothing interesting is happening, right? There's no mass coming in, there's no mass going out. It's just not changing. But because it's not changing with time, we call that steady state. But that's the boring kind of steady state. Maybe you can imagine a case where, because it's Rochester, it's raining outside, but I have a little leak in my cup, and the amount of mass that's leaving because of the leak is equal to the amount of mass that's coming in. so that the water level stays constant even though there's some mass coming in and some mass going out. That's also steady state. The equivalent of this, also because we live in Rochester, although this isn't a problem now, is, when you're driving to somewhere in the winter, right, and you get in your car and it's cold, right, so you're putting heat in, and the cabin temperature is increasing, but eventually you get to the point where the heat that you're putting in from the heater is equal to the heat that you're losing to the environment, and the cabin temperature will stay the same even though there's heat coming in and going out. That's what steady state means. It means that all of the variables in the system are no longer changing with time. Right? Another word for this is thermodynamic equilibrium. Right? Equilibrium means not changing. Right? So at steady state, the final mass is equal to the initial mass, which in this elapsed time version must mean that all the mass that came in is equal to all the mass that went out. Right? And the most boring version of this is no mass came in and no mass went out. Does that make sense? So what happens though with open systems is we tend to be less concerned with elapsed time versions of the problem, because for open systems we're more interested in what's happening, variations in space, so what's happening at the different inlets and outlets, as opposed to what's happening over time. So we typically think about rate equations, right? Or we start to look at an equation like this and think about the rate of change with respect to time. Right? So you've probably seen this in some calculus classes. We can divide all the terms in the equation by delta t. And then we can take the limit as delta t goes to 0, right? As it becomes infinitesimally small, right? And then instead of having delta t terms, right, at least on the left, instead of having delta m over delta t, we have the partial derivative of mass by the partial derivative of time. Now, there is something interesting that happens with our notation, though, right? Because the left-hand side of our equation is talking about mass that's stored, something that's stored in the volume of the system, right? So it gets this partial derivative term, right? Or the derivative term in the equation. But the mass flow in and out, that happens across the boundary of the system. So it's not a property of something in the system. It's just sort of accounting for what's crossing the boundary. So those we put dots over. Now, if you're taking a calculus class, they might tell you that x dot is velocity. That dot just means take the derivative with respect to time. And we'd use that notation sometimes in engineering too. But here we mean something different when we put a dot over something versus when we actually write out the derivative term. So when we write out the derivative term, we're talking about a property that's inside the volume of our system. But when we put a dot over it, we're talking about something that's happening at an inlet or an outlet of our system. But the units are all the same. It's all mass per unit time, right? So this is how much mass we're storing or depleting in the system. And this is the mass flow rate at the inlets and the mass flow rate at the outlets. So how fast is water coming into my cup, right? Or how fast is it going out of a hole that I drill in my cup? So now, if we talked about the words that go along with this equation, it's the rate of change of mass that's stored with the system, which if you think about this, if I put it out in the rain, it's like, how fast is the water level increasing, right? How fast am I accumulating or decumulating or depleting the mass in my system, right? And then I talk about what's the rate that mass is entering through the top of the cup, right? And the rate that mass is leaving from a hole that's drilled in the side, right? So those are mass flow rates, right? Or the net mass flow rate across the boundary. We can draw the same system, but now instead of looking at it at two different times, Now we're taking one snapshot in time and we're looking at rates, right? So now we're not talking about M2 minus M1. We're talking about the rate of change of mass in the system, right? Am I storing or depleting mass? And if I am, how fast, right? And I'm talking about how fast is mass entering my system? How fast is mass leaving my system? Right? But the concept is still the same, right? The change in mass in the system, or how fast we're accumulating or losing mass, is some function of how fast we're adding mass and how fast we're taking mass away. And we still have this beautiful steady state situation where if I'm adding mass at the same speed as I'm losing mass, then my water level stays the same. I'm not accumulating or losing any mass, even though there's always new mass coming in and there's always old mass going out. Right? So at steady state, when we have a rate equation like this is part of why we have some of these terms related with the, a system property to do with the volume. It gets this derivative term because at steady state, everything is constant with respect to time. So at steady state, I'm not accumulating any mass in the system because that would mean the mass in the system was changing. But I don't force the mass flow rate in or out to be zero. I just force them not to be changing. They have to be constant. Right? So if we're at steady state, and in this class, I think except for maybe one homework problem, we'll always be at steady state. You won't have to do the transient solutions in these problems, right? So it's like, again, if you talk about heating up the cabin temperature in your car, when you're in, you might be interested in what's the temperature of the cabin going to be once it gets to that equilibrium, once it's not changing anymore. We can find that from the steady state solution. But if you want to draw a curve that tells you, how the temperature is changing over time, then you're going to have to do the calculus, right? Or maybe a better, conservation of mass argument is, if you think about a big reservoir, right? And I know my cup's not that big of a reservoir, right? But if this was filled right to the top and I drill a hole in the bottom, it starts losing mass. But it loses mass more quickly when the glass is full because there's more water pushing to get out, right? But as the water level goes down, my mass flow rate slows down. So in a problem like that, then you'd have to do the calculus to find out the change in mass. But we typically, almost always, like 99% of the time, are interested in what's happening at steady state, after things are changing. Right? So if you're at steady state, then your mass flow rate in is equal to your mass flow rate out. Okay, so how do we solve a problem like this? Right? Now, we've talked about this for thermofluids problems, problems that you'll do in fluid mechanics or heat transfer or thermodynamics. We know the right equations, but oftentimes we don't have enough information to actually solve the equations, right? So sometimes we have to use assumptions and our understanding of the physics to see which terms are important, right? So it's always nice to say, like, yeah, we got this equation, right? But there's three unknowns, and we don't necessarily know any of them. Although if we're at steady state, at least dm by dt goes to zero. And then I need to know the mass flow rates coming in and the mass flow rates going out, right? But still, I want some kind of equation for mass flow rate because I usually don't directly measure mass flow rate, right? So now we can think about flow through a pipe, right? Now, there's this rule that we call the no-slip boundary condition, right? And that means if you think of water flowing through a pipe, it's made up of lots of different fluid elements. You can think about little tiny volumes of fluid, right? Infinitesimally small, right? And the ones that are right up against the wall, they don't move. They have the same velocity as the wall, right? But in the middle, the water's flowing pretty fast, right? So especially when the flow is slow, you get this beautiful parabolic shape here, right? So how do we find the mass flow rate through that pipe, right? What we could do is we could integrate over the radius of the pipe the density of the fluid times the velocity, which is going to be a function of the radius, over the area. Right? So if we did that, right, we'd get density times velocity times 2 pi r dr if we're integrating over r, because velocity is a function of r. Right? Now, in order to build your confidence in this equation, I want to at least show you that the units are right. So my mass flow rate should be in kilograms per second, right? Density is kilograms per meter cubed. Velocity is meters per second. Area is meters squared, right? So I got meters cubed on the top, which goes away because I got meters cubed on the bottom. I get kilograms per second. But over here, right, I got density, which is kilograms per meter cubed. Velocity is still meters per second. 2 pi is in radians, but radians kind of isn't a unit, right? And then I've got radius, so that's meters, times dr, which is like a really small length, right? So that also gets me to kilograms per second. Right? So now I can think of this, right? And I don't really want to do the calculus, right? So I'm going to make some assumptions. I'm going to assume that the velocity is not actually a function of the radius. That if I can measure the average velocity in the pipe, that's good enough. Right? And if that's true, then I could pull that velocity term out. Maybe think of it as a speed instead of a velocity. Right? If the density is constant, right, then I can pull that out too. And I get density times velocity or speed times the integral over the area, right? Or density times velocity times 2 pi times the r dr from 0 to r, right? Or I get the density times the velocity times 2 pi r squared, right? Or the area, right? I can generalize this to velocity times the area times the density. That's usually how you talk about it in fluid mechanics. But in thermodynamics, we don't really talk about density. We talk about specific volume. So one of the ways that we will define mass flow rate is if at an inlet or an outlet, we know the average velocity, we know the area, and we either know the specific volume or maybe we know the temperature and the pressure so we can find the specific volume, then we can find the mass flow rate. Right? So you won't ever have to do this derivation, but you want to know that one of the ways we can find the mass flow rate is if we know the velocity, the area, and can find the specific volume or fix the state, then we'll know the mass flow rate. Right? So you might be asking, well, I went through some, a minute or two saying like, actually, velocity is parabolic like this, right? But we're assuming that it's constant, right? So is that a reasonable assumption or not, right? And it turns out that for most practical engineering applications, we have what we call turbulent flow. Have you ever heard of turbulent flow? Or maybe it's opposite, laminar flow? The way that I like to think about this, right, is maybe when I was a kid, right, I used to play with the taps in my, my parents' bathroom, right? So if I just open the tap a little bit, the flow is like beautifully clear, But as I open up the valves all the way, it starts to almost look bubbly, right? And that's because you get this, when it's going slowly, you get this parabolic curve. We call that laminar flow. But what happens is we talked about this fluid right up against the wall. It's stuck there. It doesn't get to move, right? It has this no-slip boundary condition. But the flow in the middle is always going faster and faster. When I was a kid, growing up in Canada, we played this game sometimes called Crack the Whip. I don't know if you've ever heard about this. They probably don't let kids play this game anymore. It was especially good if you were on ice. skating. By especially good, I mean especially dangerous. And you'd have all your friends and you'd hold hands, right? And one person's in the middle and everybody else is going around, right? So one person's like the hub of the wheel and everybody else is like the spoke of the wheel, right? So everybody's angular velocity is the same, but the velocity of the person on the end of the whip is much faster than the velocity of the person at the center of the whip, right? The linear velocity. So what happens is, as you're playing this game, your grip eventually starts to fail because you've got to hold together because you've got one side's going fast and one side's going slower, and it's pulling you, and eventually everybody falls down, right? Which is not great because ice is hard, right? But it's kind of similar for this flow, right? So if you think about a small fluid element that's like right in the middle here, right? Now, it's like holding hands with a faster fluid element on the outside and a slower fluid element on the inside. And as long as the difference in speed is not tremendous, then it can just kind of deform to the side. It can like stretch out and it's okay. And it still gets this nice clear velocity. But what happens is if the velocity gets too fast on the outside relative to the inside, it starts to kind of spiral out. Right? And we call that like a vortice, right? So it starts to kind of, this fluid in the middle that's going faster gets like pulled out to the edge, right? So a turbulent flow in a pipe, the fast flow in the middle has a tendency to want to spin out to the outside of the pipe. So in a turbulent flow, you actually get a much more even velocity distribution. Now, you'll learn in fluid mechanics that we much prefer, especially, as the people doing the math, we much prefer laminar flow because you can solve the equations, right? Turbulent flow is tough because there's always some kind of, well, they call it stochastic, right? Stochastic is like a fancy word for random. I think before I talked about if you ever want to take a tough class, like controls, nonlinear controls is the hard version of controls, right? Another way you want to look for a hard version of a class is if the word stochastic is in front of it, because that means kind of random variations of something, right? So when I was doing my PhD, I had some people that were, some friends of mine that were doing like turbulence modeling. And it's tough because there's this random component of the velocity because it's kind of chaotic. It's moving in all kinds of different ways. And even though the averages are kind of, we can understand what's going on in the average sense, at any given instant, we don't exactly know what's going on with the flow. So we had some guys from, one of the, I don't think they were a hedge fund, but they were definitely like a financial house, right? Like one of these, they were interested in trying to model the stock market so that they could, make better trades, right? So they were also interested in stochastic modeling because even though over long terms, we have this average growth rate of, say, large U.S. companies is something like 7% after inflation over long periods of time, on any given day, it could be, like I think today was kind of crazy. The S&P 500, which is like a weighted average by size of the 500 largest U.S. companies, was down like 3.5% this morning and finished about even, because it's kind of random, right? Because, the short term, it's sort of, well, anyway. Usually in my classes, I do like personal finance stuff too, but I think we're a little short on time, but I might put out videos of that kind of stuff too. But there is some randomness going on here. But the moral of the story here is for most engineering applications, we have turbulent flows. And turbulent flows tend to have pretty average velocity profiles, where the velocity profile in the pipe is pretty consistent, right? So it might change, especially near the wall, but you have a sort of a slug in the center where it's pretty constant, right? So it's not a terrible assumption. So now if we talk about this mass conservation equation, where we have the rate at which we're storing or depleting mass is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out, if we substitute in this new definition for mass flow rate as velocity times area divided by specific volume, then this equation looks like this, right? So if I know the velocities, the areas, and the specific volumes at all the inlets and the outlets, well, then I can figure out whether or not I'm adding, or the rate at which I'm adding or losing mass, right? And again, if we have steady state, that just means that the sum of the area times the velocity divided by the specific volume at all the inlets is equal to the sum of the area times the velocity over all the specific volumes at all the outlets. So that is all that I wanted to talk about today. Next class, we'll do an example for conservation of mass. We'll at least introduce the idea of conservation of energy. We may or may not get to an example because, like I said, I want to leave about half of the class time for just questions about the exam. So if you look through homework type stuff and you just have questions about, I sort of have trouble with these types of questions, or I have trouble with this specific question, then you can ask me in class. I'll also be available in my office hours on Friday and on Monday. And if for some reason you'd like to meet at a different time than that, we can try to work something out as well. Does anybody have any questions before we sign off? Awesome. Well, thank you for sticking with it. I know it's a long class. I will see you all in a couple of days. Take it easy.
Thanks so much. Have a great day.
Yeah, you too.
Thanks so much. Have a great day.